Welcome to the second part of this video tutorial series. Now I will step into the first part of the code, but at first it's very important to show you how the folder structure on your computer have to look like. I hope it is understandable what I did here. So I have the following structure. So I have in one main folder, in the folder the exercises, and under exercises I have the folder assignment 2. And in this assignment 2 is my main script. In the same folder where the folder exercises is a folder called model. And in this model, we have our IFC files. And for example, we have there our model.ifc and that what we get later, the updated model.ifc. This is important, this structure, because we used copyright information and the raw model shouldn't upload it to GitHub. So that's why you will never find in the GitHub repository the IFC file, and the code will search the source file in a folder called model that is outside of the main folder where the script is in. Now we can go into the code, and of course also we have to do it. At first, import all necessary packages. Here, for example, we use, of course, IFC OpenShell, but also for the mathematical operations, we use NumPy, for example, and the matplotlib for the plots. As I mentioned before, here we have our model is in another folder, so that means we have to go back into or step up some folders in the directory path, and that is something we do with the code that we got from our teaching assistant Martina, and we added it a bit. So because in our, and that's something I missed here to say, we have here honestly is a folder called src, and this file is, the script file is into this folder. So, and that's something I missed to tell you. So honestly, that's the folder structure. The folder structure looks like that I have in one folder. I have the folders exercises and model. And then in exercises, I will find the folder assignment 2. That's the folder that's uploaded to the GitHub repository. And in this folder, I have a folder called src for source, and there are my Python scripts in. And for that, we have to go 2 steps back to find the folder model, and that's what we did here. We see the file, and then we go 2 folders back or up in the path and find the folder model. And then that's important why you have to type in the model name or the file name. That's the file name plus .ifc, and then the code will find it. If not, we get an error. Yeah, let's start with the main script. At first, we just count elements. It was one of the first things we did by filter by type, and then we filter all beams, all columns, or all slabs, and then we count it together and print it in the terminal. The second part, or the second step here, that's not the second part like in the last video, it's that the main tool starts. So at first we have to create 3 lists. The list beam values, the list column values, and the list material lists. And then we can start to fill these lists. And that we did by the main code here. Here we have, we say, okay, we have now a variable that calls the function getBeamValues. That's this first function we defined here. And the same we did for columns, and we did it for the materials. So when we call, and that's the same for beams and columns, so I just make it for the beams now. We call the function getBeamValues. We go through this model and filter by type IFC beam, and then we collect different properties from the file. The first thing we want is the ID, so we can compare the dictionary entry what is stored to the list and find all the values we got from the code compared to what we see in Blender, for example. So to find these elements easier, we extract the tag. Then we also extract X, Y, and Z position, but here it is not so important to use that one because that's the original position where the element was created. So that's not the position where the element really is in the model now. Then we extract the cross section also by some code examples you find in the documentation of the IFC OpenShell documentation. The same for the material, the length, the settings, the shape, and the matrix. The matrix is here more important. It's where we get the rotation matrix from. And then we have something where we have our own functions. And we start here with plane. That means we want to know in which plane the beam or the column is, because we want to figure out the direction of it to calculate the start and the end points. Then we also get a mesh. Then we have a mesh center, or we get the mesh center. And then in the last step, we calculate the start point and the end point for one element. And then we wrote all these information we collect here into a dictionary. And after we have it in a dictionary, we say beam values, which is our list, dot append beam. So we add this dictionary called beam to our list beam values. And then we return beam values. That's the main script part. And now I would explain a bit more about the get beam plane and the get element coordinates, get mesh center, and add. So I dig deeper into other functions. I will start with the get beam plane function. Here we also, and that's the most important part for that, we get the vertices from the beam and the matrix from by IFC OpenShell. For that, it's a simple code you can see in the documentation of IFC OpenShell. Then here we extract the words, then we group it. We get our rotation matrix and our local direction vector. Then we say, okay, the maximum difference between an X direction and Y direction and Z direction is 0. And then we start, and that's the whole magic how this function works. As I mentioned before, our goal is to know in which direction the beam or the column extrude. And for that, we look for the biggest difference in one direction, in X, Y, or Z direction. So that's what we did here. Just looking for the biggest difference. And then we look, is this difference X bigger than the max difference X we have here? If yes, say max difference, max diff X is equal to diff X. And then we have our new maximal difference in X direction that we did for Y and Z. The same. And then when we go through this list of words, we say, okay, now we want to have it into the biggest difference, and we look for the maximum values. So we sort it into the biggest one. And now we are looking into, we're calculating the global direction vector. And that's something we do with this part, and then the second part if we have a slope. So in the first part, the slope is 0. That means if the beam or the column is horizontal or vertical, we don't have a second direction because we don't have a slope. And then it's very easy. We're just looking what is in which direction is the maximum difference. And then we're saying, okay, plane is X, or plain value is 1, because I did both because it was easier for the code, and that's just for checking, because when you have your normal X, Y, and Z axis, it's easier to confirm that what the script does is right. And now we know in which direction we are, and then we can say, okay, when the plane value is equal to 1 or the plane value is equal to 1, 2, we can calculate the local direction with this function. If it's in Z or in Y or Z direction, we can calculate by this. If there is no plane found, we get a small error printout with the element tag, so we can find it. And now we can calculate our global direction by multiplying the rotation matrix we get just from IFC OpenShell with our local direction vector. And then we return the plane value, and of course the global direction. And this whole step we did also when the beam over the column has a slope. So we're looking for the first and the second biggest difference. And it's the same like here, just we did it twice. So I will skip it now. So the next function we created by our own is to get element coordinates. It's the mesh. Get element coordinates. It's this one. The first part is the same. We extract the vertices, group them, get a matrix, and so on. And then we create a mesh from our element, and from that one we get the absolute mesh coordinates. So in the last step we got the plane, and now we have the absolute coordinates of the mesh, and then we just give the mesh, the absolute mesh, back to our variable here, and say, okay, now we want the mesh center that we get, reach through the get mesh center function. The get mesh center function is this. It's very short. It's a Python built-in function. The mesh center is the middle point of the mesh, and then we return just mesh center. And now we are coming to the big goal, to extract the start and the end point from the elements, and that's to get start point beam and to get end point beam function. We have the same for columns, so I just go here into the beams. I open both. So we see here start point beam is the mesh center minus length divided by 2000 multiplied by the direction. We need 2000 because the first factor, the 1/2, is to get the half of the length, to going from the middle point of the mesh to the start and or to the end. And then we need the factor 1000 to convert it from millimeter to meter, because the mesh coordinates are in meter, but the length that we get from IFC OpenShell are in millimeter. And then we do the same for the endpoint. We just add, say, plus instead of minus. And now we have everything collected, have everything in the beams and in the columns, and say, now we want the lists. So we open a text file into, and that's the same. We say here we go from our script one folder back, search for the folder results, and in this folder this beams. And then we write for each element in beams, that's this one, write as a string the element and go then in the next row. And then we do it for the columns and also for the materials. When we have printed our lists, we want to see a bit of that, what we did. And the easiest part for us was just to create a simple 3D plot. And in this 3D plot, we plot all start and endpoints and connect it with a line between the start and the endpoint, label the axis, and just show the plot. If you don't want this plot, of course, you can just comment that one out. And the last step here is to create a new IFC file for the simplified model. We create a new empty IFC file, so we call it simplified model. And here it's important, IFC4. Then we create a new list, nodes. And then we store into this list all the start points and the end points from the beams, or the start and the end points from the columns, and write it down. Now here in the text file, in the future hopefully also in an IFC file. So then I will run the script up to this point, and you can see how that looks like. Here you see how many beams we have, how many columns we have, how many slabs we have. We see that the script doesn't find a plane for the element 1803584. Okay, now we can go into Blender, search for this element tag, also for the second element tag, and look what happens, what is wrong with it. Now we see that the lists are created. And here comes the figure, our plot. So honestly, it is not made to plot something like this, but I hope you can see it like I can see it. I would say it looks like our Blender BIM model. And we see a lot of vertical, a lot of horizontal, and also here we have some beams with a slope. So everything is in. And because now I go back to the script and end the plot, we also created the new IFC file simplified model.